In the last lecture, we have started discussing the motion of a rigid body in space. It has been found that the motion of a rigid body in space can be split into two parts: a pure translation and a rotation about a point. We have also seen that the part which contributes to translation is very similar to the motion of a particle, and the whole body can be assumed to be concentrated at a point. On the other hand, it is now necessary for us to analyze in details that part of the motion of the rigid body which is about one point. It has been further shown that when a rigid body is moving with one point fixed, the motion at any instantaneous position or at any instant can be considered to be a rotation about an axis passing through that point. Thus, if this be the rigid body and this is the point about which it is executing rotation, then at any instant of time the body can be assumed to have a rotation about an axis, and instantaneously the angular velocity of the rigid body can be expressed or represented by a vector omega along the axis about which it can be considered rotating at this instant. It should be also remembered that this angular velocity vector is neither fixed in space nor fixed with respect to the material body. This executes a motion with this point O fixed in space, generating a cone which we call the space cone, say for example this, and so far as an observer attached to the body is concerned, with respect to the body this vector also executes another cone which we call the body cone, and the motion of the rigid body is equivalent to the motion generated by a pure rolling of the body cone over the space cone, and at every instant the line along which the two cones are in contact is the instantaneous axis of rotation, and the instantaneous angular velocity is along that. Today what we will do first is discuss about the angular acceleration. Now, what is an angular acceleration? Angular acceleration we know is the rate of change of angular velocity. Now, we should define a bit more clearly that if we have a frame of reference x, y, z which is fixed in space, and if this be the angular velocity vector at an instant, then angular acceleration is the rate of change of angular velocity omega with time as observed by an observer fixed in this fixed frame of reference. Now, we have seen that this angular velocity vector, since it is a vector, it can change either by its change in magnitude without changing the direction. It means it can remain same in its orientation, only its length will increase, or it can remain constant in its magnitude, but the direction of this vector will change, or in general both happening simultaneously. To find out the rate of change of this angular velocity vector, therefore, what we do is we first consider a frame of reference small x, y, z with the origins of the two coordinate systems coinciding all the time. This angular velocity or this frame of reference, in general we may assume that it has an angular velocity capital omega with which this small x, y, z is rotating with respect to the fixed frame. Then there are two observers, one fixed to the capital X, Y, Z frame, one attached to the YOLO X, Y, Z frame, which is not fixed in space, which is having a rotation with an angular velocity omega with respect to the fixed frame. So, now if there is any vector A, its rate of change as observed by an observer in the fixed frame of reference dA dt capital X, Y, Z can be represented as the rate of change of the same vector as observed by an observer small x, y, z plus the effect due to the rotation of small x, y, z frame. So, see that if this vector A we are talking about is rigidly attached to the small x, y, z, then to an observer in x, y, z, small x, y, z, this vector will have no change. The observer sitting outside will observe a change because this vector is rotating along with this moving frame of reference with this, and from vector calculus we know that this rate of change can be written as this. So, the angular velocity vector omega will also have the same equation fulfilled, that rate of change of angular velocity as seen by a fixed frame of reference is the angular acceleration by definition, and it will be equal to So, this is the general expression for angular acceleration of a rigid body for a motion about a point O. Now, I think to explain this better, let us consider an example. Let us take this cylinder that is mounted on a shaft, and the shaft is again mounted horizontally, in this case on a vertical shaft, which is rotating with an angular velocity omega 2. So, the whole drum or the cylinder is being carried by this horizontal arm, which is rotating with this angular velocity. At the same time, we provide a rotation about this horizontal axis with an angular velocity omega 1. So, as you can see that this point which is on both the axes is fixed in space, it cannot have any motion. Now, what is the angular acceleration of the cylinder? Let us find out. So, what we will do? We will do the same way. We will have one frame of reference which is fixed, say this is the fixed frame of reference with this point as O. This is the moving frame of reference, momentarily coinciding with the fixed frame of reference capital XYZ. The angular velocity components, that means the velocity of the body about the shaft, is omega 1, and velocity of the shaft itself or the axis of rotation itself is omega 2. Now, what we do? We consider this small xyz frame to be rigidly attached to this horizontal axis carrying the drum. So, therefore, this omega 2 is nothing but the angular velocity of this small xyz frame, which is rigidly attached to the shaft carrying the drum. So, now from this relation, that angular acceleration of this can be written as so next, therefore, next you have to find out what is the angular velocity of this drum. We have seen in the previous lecture that at any instant the angular velocity of the drum is nothing but the vector sum of the two components. Or so, substituting this here, we get because omega 2 cross omega 2 is 0. So, what remains there is only omega 2 cross omega 1. If we consider a situation where the magnitudes of the angular velocity components omega 1 and omega 2 are constant, then we will find that both this term and this term will be 0, because there is no change in omega 1 as observed by an observer sitting on the moving frame of reference, though with respect to fixed frame it is changing direction, but an observer sitting with the moving horizontal shaft will not see any change in the angular velocity omega 1. So, this will be 0. Similarly, this observer will also not see any change in the omega 2 angular velocity component. So, that will be also 0. So, this in a particular case where omega 1, omega 2 are constant, under that condition it will be simply, we can simplify further in this way. We can represent omega 1 and omega 2 in terms of the unit vectors along this. So, unit vector along small x will be I, unit vector along small y direction is j, and unit vector along the small z direction will be k. So, omega 1 is equal to as per this is minus j omega 1, both its z and x components being 0, and omega 2 is equal to k omega 2, other two components, that is x and y components being 0, and the angular acceleration will be and this is equal to k cross j, which is minus I, and this minus and that minus can becomes positive 1. So, angular acceleration of the drum is given by this, and you can see it is directed towards x axis, it is also a vector. So, this completes our discussion on the motion of a rigid body. Particularly, we are interested in the motion of a rigid body with one point fixed, as we see that any general motion can be split into two parts. One is the translational motion of any point on the body and a rotation about that point, and the translational part is trivial in the sense that it represents a particle like motion. On the other hand, the motion due to rotation needs further investigation. Therefore, let us now take up the question of the quantity of motion in a rigid body when it is executing a space motion with one point fixed, or in general a space motion. So, before we discuss the dynamics, we know that we have certain quantities which represent the magnitude of motion, that is momentum, that is the general definition. So, there are two kinds of momentums we know, one is linear momentum, other is the angular momentum. Now, again this is a quick recapitulation of our knowledge of dynamics. We are not going to have detailed discussion, we will only derive the basic relations which we will be using for analyzing or studying the dynamics of machines or machine components. Now, here you know that a rigid body, during its discussion on kinematics we have mentioned that a rigid body is defined by a collection of infinite number of infinitesimally small point masses whose relative distances remain unchanged. So, what we can do, we can consider just one is such infinitesimal mass, say dmi, and if its velocity be vi, then the linear momentum of this particle is simply and if we sum up this quantity for all the particles constituting the body, we will get the linear momentum of the rigid body. So, if we use symbol p to represent linear momentum, of course it is a vector, so it is p vector, we have to just sum it up for all the particles. Now, we have seen that we can treat the motion of this rigid body as a translational motion of a point and a rotation of the rigid body about that point. So, this rigid body's motion will represent that a point O, it is having a velocity v o and a rotation of this rigid body instantaneously about an axis and its angular velocity at this instant being omega. If this be the case, then a particle of mass dmi at a location from this fixed point, say rho I vector, then we know that velocity of this with respect to this point is given by omega cross rho. So, therefore, the total velocity of this point will be velocity of the point O plus omega cross rho y. So, the velocity of this point V O plus the velocity of this particle with respect to this point, which is given by omega cross rho y, and we know that any velocity between 2 points on a rigid body has to be due to rotation, because the distance between the 2 points cannot change in a rigid body. So, with this we can write now P is given by summed over I all the particles summed over all the particles. Now, in this case we find that this summation is over all the particles, where this V0 or VO rather is common to all particles. So, we can take this VO outside and sum over all the particles their mass, which is nothing but the total mass of the object, plus omega cross, just a moment, here also we can see omega is constant for all the particles. So, we can take omega term outside the summation and we get this. Now, if this particular point O we have chosen happen to be the center of mass, if this happen to be the center of mass, then by definition of center of mass this term is 0, and therefore, the linear momentum of a rigid body is the velocity of this point, which is now the center of mass g rather than being any point, into m, and this part is 0. So, in effect the linear momentum of the rigid body is represented or is determined by the consideration that the whole body is concentrated into a particle of point mass at the center of mass of the body, or this is nothing but the linear momentum of a particle located at the center of mass having the same mass as the whole body. This is an interesting result we have seen. Now, find out the angular momentum of a rigid body. Now, when we talk about angular momentum, you know that we must have a point about which we consider that angular momentum. Unlike linear momentum, which can be defined without any reference to a specific point, but in case of angular momentum, we need a reference point about which we are defining the angular momentum. So, therefore, first let us find out the angular momentum of a rigid body about a fixed point. So, this is the rigid body, and we have seen that the center of mass G is a very convenient point for defining certain quantities, as you will see. So, we first define its distance from a fixed point O by the vector r g, and the particle under consideration dm I, which is at a distance rho I from the center of mass and at a distance r I from the fixed point O. Then the definition of angular momentum tells that angular momentum of this particle about point O, so dLO I, if we define that as the angular momentum of this elementary mass about this point, will be equal to the linear momentum of this, which is and the moment of that linear momentum about this point, which is given by. So, this is the moment of linear momentum of this particle mass, and to get the angular momentum of the whole body about this, we have to only sum it up for all the particles constituting the body. So, LO will be summed over all the particles. Now, we have seen that the point of this mass can be also represented by the sum of two vectors. One is the position of the center of mass r g plus its location with respect to the center of mass rho I. If we do that, this represents this cross now again the velocity of this point we know can be represented as velocity of the center of mass Vg plus the velocity of this point mass about with respect to this, which is given by where omega is the angular velocity of the body with and rho I is the distance or location of the point mass with respect to the center of mass. If you substitute this, then the angular momentum about point O will be given by so, it is a straight substitution of Vi term there. Now, if we expand, you will get Rg cross Vg dmi plus Rg cross omega cross rho I dmi summed over I plus rho I cross Vg dmi and plus so after expansion we get these four summed up terms. Now, let us examine these four terms. So, here you find that Rg, Vg, they are all constant and they do not change or depend on the particle we are considering. So, the summation can be taken and this represents nothing but Rg cross Vg into m, that is the linear momentum of the object. As we have seen, linear momentum of object is nothing but Vg into m. The second term, you see that this is something which does not depend on the particle, omega also is constant. So, the summation will be taken over here, and by the definition of center of mass we know that sum rho I dmi is 0. So, this term will vanish. Same will be the situation with this, because Vg is constant. So, what we can do, we can take dmi here and do the sum and then take the cross product with Vg, and again by definition the sum dmi rho I is 0. So, the other term which remains will be so thus angular momentum of a rigid body about a point O is given by this. Now, we consider two more situations. This is a perfectly general case. Two more cases where the motion of the rigid body about point O as a fixed point, let us take that case. Now, as I said, let us consider this case where a point O of the body is fixed in space and body is rotating about this point. So, this is a simpler situation, and the particle mass dmi is considered to be at a location Ri with respect to this point O. Then its velocity will be simply omega cross Ri, and the angular momentum about O will be so. Therefore, straightforward we come to this expression from the definition that it is nothing but the moment of all the linear momentum of all the particles summed over the whole rigid body. If O happens to be the center of mass, then the angular momentum of a rigid body about the center of mass summed over all the particles. So, these are the two cases where a point on the rigid body is fixed, and in a special situation when that particular point is the center of mass. We will require these expressions at a later time. Now, let us come to the question of the inertial properties. We know that in case of simple fixed axis rotation of a rigid body, the inertial property of the body is defined by a quantity we call moment of inertia, which is nothing but the second moment of the masses of all the particles about that axis, and angular velocity into the moment of inertia gives us the angular momentum in case of planar rotation, as we have seen. So, let us now investigate little bit about the inertial property of a rigid body in space motion. So, if we take the angular momentum of a rigid body, now if the particles be infinitesimally small and the number become infinitesimally large, then we know that this summation can be represented or replaced by integration over the whole body. Now, we would like to have a more clear definition, or rather in more concrete terms, this quantity. To do that, let us consider these position vectors R in terms of coordinate of the position of a point, which is simply if x, y, z be the coordinates, we have to fix up a coordinate system on the body. So, any point, its location will be x, y, z, and the vector r will be given by this, where I hat, j hat, k hat are nothing but the unit vectors along the axis x, y, and z respectively. Similarly, vector omega will be also expressed in terms of the three components: omega x, omega y, and omega z. Now, with this term omega cross r becomes, now when you take the cross product, then I cross I is 0, I cross j is k omega x y, plus I cross k is minus j omega x z. Then next, j cross I is minus k omega y x, j cross j is 0, j cross k is plus I omega y z, plus k cross I is j omega z x, plus k cross j is minus I omega z y. So, this is equal to I omega y into z minus omega z into y plus j omega z into x minus omega x into z plus k into omega x into y minus omega y into x. This is omega cross r. Now, if we take this term r cross omega cross r, then we have to again pre-multiply this by r. So, it will be I cross I is 0, I cross j will be k, and this x into this. Next will be I cross k will be minus j omega x x y minus omega y x square. Next, let us take j cross this, j y cross this. So, this will be plus j cross I is minus k into this into y, that is omega y y z minus omega z y square plus j cross k that is plus I into omega x y square minus omega y x y. The last term will be this cross this. So, k cross I is plus j omega y z square minus omega x omega z y z plus k cross j is minus I to omega z x z minus omega x z square, and k cross k is 0. So, that term goes. So, this is the term. Let us put it in a neater form. So, we can say that over the whole body can be written as I omega x y square minus omega y x y minus omega z x z minus omega x z square. So, it will be omega x into y square plus z square dm. That is one term. This is minus omega y x y dm minus omega z x z dm. Plus j omega y z square plus omega y x square. Next, omega z y z minus omega x x y. So, this is the jth component of the angular momentum, remember that, plus k, that is the z component, k into omega z x square plus omega z y square, this minus minus makes plus, minus omega x omega x x z minus omega y y z. Okay. Now, let us see what we have got. So, here if we further examine, we will find this is nothing but I. Now, omega x component of the rotation or angular velocity of the rigid body, it does not depend on particle to particle. So, it can be taken out. If I take out this, then what remains inside is dm into y square plus z square. You all know that if the particle be here, then y square plus z square this is y square, this is y and this is z. Now y square plus z square is nothing but the perpendicular distance of this point square of that about x. So, mass of this particle into distance square from x, if you sum it over, then it is nothing but the moment of inertia of the rigid body about the x axis, and we denote it by Ixx. So, this is nothing but omega x into Ixx minus this omega y can be also again taken out because it does not depend on the particle position, but this quantity xy dm, that means the product of the x and y coordinate of this point multiplied by its mass summed over the whole thing is something which we not encountered before, and we call it a product of inertia Ixy. And similarly, this will be another product of inertia Ixz. So, the ith component looks like this, the jth component will look like this, minus I minus I omega I xy omega x plus, this is again nothing but the moment of inertia of the rotating body about the y axis, and we define it by Iyy, and the third remaining term, this one is Iyz omega z, and the k component is minus, this integration is nothing but I xz or zx omega x, this term is nothing but I zy omega y, and this term is nothing but the moment of inertia about the z axis I zz omega z. So, we can also see from here that this product of inertia terms, that Ixy and Iyx will be same, Ixz and Izx are same. So, it is a symmetrical situation. So, therefore, now you find that in a slightly more compact form, the components of the angular momentum vectors can be written as this. Now, we should also see that angular momentum of the object is a vector quantity. Now, angular velocity is also a vector quantity. So, here you could represent in matrix form So, if you write in matrix form, we find that this column matrix, which is representing the angular momentum vector, is a product of this square matrix, which represents the inertia of the system multiplied by the column matrix representing the angular velocity vector. So, we come across a new quantity, that angular velocity vector is a product of a quantity I with angular velocity vector omega. Now, this cannot be a vector, we can see, because the product of two vectors are either a scalar in case of dot product or a vector in case of cross product, but it is always at right angles to the two vectors whose product we are taking. But in this particular case, there is no such compulsion. So, this quantity is something different from a vector. It cannot be a scalar also, then the two vectors would have been in the same direction, and we call such quantities, which are represented by a matrix of 3 by 3 matrix, we call this is a quantity which is of a higher level than a vector, and we call it a tensor. We need not bother much about the tensor, except for the fact knowing that this inertial property of a rigid body needs to be defined by a tensor. It cannot be defined by a scalar, as in case of a particle or planar rotation of rigid bodies, nor can it be represented by a vector, something higher than that, and that is why we call it the tensor. So, angular momentum of a rigid body is inertia tensor with that point O as the reference point multiplied by the angular velocity. Yes. It is a very complicated situation, as you can see, and handling this kind of expressions is not very convenient, but we are lucky in one sense. In case of all rigid bodies, it can be proved, we need not go into the proof, it can be proved that we can always select the x, y and z axis in such a manner that the products of inertia vanishes, and these set of axes are called principal axes. So, if we align this mutually perpendicular 3 axes x, y, z along the principal axis, which always exist, then the products of inertia will vanish, and the angular momentum vector can be then represented into 3 components. 3 components will be I x x omega x, I y y omega y, so it is a very happy situation. The expressions are much simpler, but still we should remember that it is still a tensor, and or in matrix form still we need to have a matrix and even in such a situation we have to keep in mind that the angular momentum vector and angular velocity vectors do not coincide, except for this special situation where I x x, I y y and I z z are all equal in magnitude. So, even for the simplest possible situation where we represent the whole thing with reference to the principal axis, the angular momentum vector and the angular velocity vector, they will not be same. I think this gives us some idea about the inertial property of a rigid body. We find that it is a very more complex situation than a particle or simple particle or even planar motion of a rigid body. It needs in general 6 independent elements Ixx, Iyy, Izz and 3 products of inertia, because this is a symmetric case. Now, I think when you go to the discussion on the dynamics of a rigid body, then obviously we have to now find out the rate of change of this momentum, which we have found out, and found out the expressions which we intend to take in the subsequent lecture.